Okay, everybody, here we are, Calc Day 16, Chapter 5, Section 2. This section has some really cool illustrations in it, so I'm going to try to use the book and take some notes on the side here. So we had just finished looking at areas underneath a curve and using rectangles and finding the limit as it approaches infinity to find the approximate area that we could get to underneath that curve. So now we're going to look at volume with a similar kind of strategy. First, let's take a look at some volumes. Here we have a volume of a cylinder. This can be considered a cylinder where we have the area of the base times the height. So it's like stacking this base all the way up. Here's a regular cylinder again. Now the bottom of this base is a circle. So you have pi r squared times the height. And here we have a rectangular base. And so we would take our length times our width times our height to get our volumes. Now sometimes our figures are not that nice and neat, and sometimes we will be using the function of x to describe some of the barriers. So how would we approximate that? Excuse me. Here we have a very odd looking shape, and we can see, let's pretend this is a slice of, or this is a loaf of bread. This is what it looks like to me. And we're slicing portions out of this loaf of bread. Now, just like before when we used rectangles, when the shape really underneath it wasn't a rectangle, we're going to do something similar here. And we're going to use a cylinder. And we're going to estimate cylinders along here so that we can estimate the volume, and that cylinder would have some kind of thickness. So for instance, let's take a look over here. I'm on page 353, by the way, and here is a good example. Here's our slice of toast that we're having, and we have our distance xi minus 1 to xi right here, and then we have our center of that just as before, maybe a place in the middle that would give us a better estimate. Now we also have our width and our thickness here, which would affect the area times the thickness. The thickness in this instance would be similar to height. So we have the area of this figure here times the height, and then we would add all those together. Now, just as before, the more area, or the more you slice it up, the more you are going to be accurate. So we can see here, if we just slice it up to 7 pieces, 1, 2, 3, 4, 5, 6, 7, you can see that I'm going to be missing some gaps. However, I can use the same strategy as I used before, where I'm looking at Riemann sums, and I'm going to add lots and lots of these. And as a matter of fact, I could say as limit approaches infinity, that area times the width, which would give me the volume, as n approaches infinity, and that means an infinite number of slices. It would be nice to have an infinite number of slices of bread, but they'd be awful thin. And from your bounds here from A to B. So let's look again at this. So we have our area times our width, and then we're looking at this from A to B. As it approaches infinity, will give us that volume of that solid. Now, We do need to make sure that it is a continuous function. We don't have any large gaps or holes in there. And if that's the case, then we can use this. Now, sometimes we'll be able to recognize the actual figure. So for instance, we're going to look at this sphere down here, and we're actually going to prove that the volume of a sphere is 4/3 pi r cubed. First, let's take a close look at this. If I set a sphere at the origin, and again, I'm doing that because I want to, because it's going to make it easier for me. I can take a look at what my radius would be by inscribing a triangle in here and using the Pythagorean theorem. This distance is x, this distance is y. And when I do that, I can solve for the radius. So, from Pythagorean theorem, I'm going to flip the page here. We will see once we solve for our y value, y is going to equal the square root of r squared minus x squared. So the cross-sectional area is going to be pi r squared because it's a circle, and I just said that my radius is this. So this squared would get rid of my square root and leave me with this. Now, I notice that my sphere is an even function. So if I put it at the origin, I'll be measuring it from negative r to r. And go ahead and substitute in our formula here. The interesting part of this is because it is symmetric, I can now just take 2, I'm going to move my pi out because pi is a constant, from 0 to r to solve for my integral. And that goes back to our even functions that we looked at before. So now I'm going to go in with respect to x, and I'm going to integrate. And when I do that, I'll get r squared x minus x squared over 3. And then I substitute in my upper and lower bounds. And once I simplify everything, I will in fact find that the sphere volume is 4 pi r cubed. Pretty neat. Okay. Now, let's take a look at this figure here. Again, emphasizing that we can break down using so many discs. We'll say we take that sphere and we just use 5 circular cylinders. What about if we use 10? And what about if we use 20? So again, the more that we have, the closer and closer that we're going to get to that shape. And anytime we say closer and closer, we know that we're going to be looking at a limit as it approaches infinity. Okay? All right, so now this next one, example 2, looks at y equals the square root of x. Now at this point, you should know your parent functions. You should know what this looks like right away. You can say this goes like this. And actually, it's on the next page too. We'll look at how we're going to use it. So we're going to look at this region by rotating it about the x-axis. Now this is the x-axis, so I'm going to rotate this like this. Okay? And we'll get a solid, and then we slice through point x. We'll get a disk with the radius. The radius is going to be this edge, which we know is the square root of x. Okay? So our area would be pi r squared, and our radius is going to be the square root of x squared, so it's just pi x. Now to find the volume, I'm going to have to multiply that by the thickness. So I multiply the area that I already have by my thickness. So I'm going to go to the next page and we're going to take a look at a much better drawing than I can do. Here it is. This shows us that we have our curve from 0 to 1. Here it is, rotated about the x-axis. And you can see our disk here. This is just one example of a disk with a thickness of delta x. So knowing that, we have our pi x dx, and we're going to integrate that from 0 to 1. 0 to 1, that's the bound that I'm looking at. And I will end up getting the value of pi over 2 just by doing the simple integration on these last two problems. Okay, now we're not always going to go about the x-axis. We might go about the y-axis, and when we do, we might have to solve our equation for y before we integrate it, and that shouldn't be a problem. So let's take a look at y equals x cubed, which looks like this. Okay, and let's say I'm going to examine it from 0 to 8. So this part, and I'm going to spin it around the y-axis. Now, the area of the cross section is going to be a circle, and that is going to be represented by x equals the cube root of y. Why is it that way? Well, because we are looking at it with y bounds. So I have to take this and solve it for x. So I take the cube root of both sides, and that's how I get the cube root of y. So my area of my cross section is going to be pi r squared, and my r squared in this case is the cube root of y squared. So I'm going to have pi y to the 2/3. Again, this is just my area. So now I have to have delta y, which is my thickness, and it's delta y again because we're going along the y-axis for the thickness. So I have delta y. So I have pi y 2/3 delta y. And then I'm going to look at from 0 to 8. So taking a look at the volume, I just plug my values in, integrate it, so I get y to the 5/3 over 5/3, which becomes 3/5. And I can take my 3/5 pi out and then plug in my 8 minus, and this will be 0, so it wipes that out. So I just have to plug in my 8, which is, again, another reason that we might choose to put these figures at the origin when we're measuring them so that it's easier for us. I mean, it doesn't matter whether it's at the origin or whether we move it up or down, but we might as well make it at the origin so we have this 0 down here that we can deal with. Okay? Alrighty, so now that's example 3. It's 96 pi over 5. Let's move forward. Get some really neat looking figures here. Here we have a region that can be closed by more than one function. So here I have y equals x, this line. And then here I have y equals x squared. And again, these are parent functions. You should know how those look right away. You shouldn't have to put them in a graphing calculator. If you're not sure of your parent functions, I believe they are in your book. There's some in the back here. Okay, in the back of your book for special functions. Let me see if there's some in the front as well. Here we have some volumes. So there's a lot of information here. You should take some time to study these because this is supposed to be common information at this point. Okay, so here we have, now let's look at this. It says we're going to rotate it about the x, so we're going to rotate it like this. Okay, so if I rotate it like this, I need to pay attention to which one is on top and which one is on bottom. So looks like my y equals x is going to be on top, and then my y equals x squared is going to be on the bottom. So as I make my circles here, I'm going to take the outside circle minus the inside circle so that I can get this, we call it a washer, the shape of a washer or an annular ring. Okay, so again, you might say, well, you know, what about that line is kind of curved there? Well, remember, we're going to infinity with these, so they'll be really, really small. So that would be the best way that I can find my volume. And here's a nice picture of it here where we're showing our x squared. This is our y equals x squared. Our parabola is on the inside, and our straight line is on the outside, which is y equals x. All right, so again, area of the circle is pi r squared. So if I'm going to take my outside, which is a line, minus my inside, which is a parabola, I have pi x squared, because it's pi r squared, minus pi x squared squared, because this is my parabola. So this is my parabola, and this is my straight line, and I'm putting it into the area of a circle. I can factor out my pi value here, and then I have x squared minus x to the fourth. So I want to take that area, and I want to integrate that from 0 to 1. And when I integrate it, I will be adding my delta x. Integrate. X cubed over 3 minus x5 over 5. Evaluate from 0 to 1. And when I do that, I'm going to get my 1/3 minus my 1/5. And then 0 for the second part. And when I simplify it, I will get 2 pi over 15. Okay. Figure 8. This is figure 8. It shows these three. Now let's go to example 5. Find the volume of the solid obtained by rotating the region. In example 4, about the line y equals 2. So I can look at these differently. So again, this is my y equals x right here. And right here is my parabola, y equals x squared. I'm going to place a line at y equals 2, and I'm going to rotate this about the line y equals 2. Why would I do that? Well, maybe I need to make a certain size washer in a machine shop, and I need to calibrate the program to do that. So here, things are just a little bit different now. I have my y equals x squared is not on the x-axis. It's up here. It continues to move depending on where we're going to slice the washer. So there'll be a little bit of a distance between here and here. This is going to be my x squared value because that's where my parabola is. And from here to here is going to be my line, which is my x value. Now, if I'm going to measure that from y equals 2, then I take my value of 2, which is this whole thing, and I subtract my x squared, so I get 2 minus x squared. Same over here when I look at the whole thing and I subtract my x value. So when I take a look at these this time, I have to realize that I have my 2 minus my x squared minus my pi times 2 minus my x squared. This time my parabola, oh, I'm sorry, I didn't have this down far enough. Okay, my parabola is on the outside, so it's going to be my bigger value, so I need to have it first, minus my line. So I'm going to take a look at this from 0 to 1. Now you say, well, where's the 0 to 1? The 0 to 1 that I'm looking at are my x values here. I'm looking at this washer that I'm creating from 0 to 1 that I am rotating at y equals 2. And I've already taken care of the y equals 2 part when I took a look at my distances over here, and 2 minus x squared and 2 minus x. And you can see those in here substituted in for the area. So now I have my area, pi r squared, and I'm going to subtract. So I'm looking at it from 0 to 1 of my area dx because I want to find my volume. And I can factor out my pi value, and once I factor out the pi value, I can multiply this out, and again 4 minus 2x squared plus x to the fourth, and then minus 4 minus 2x, no, make that 4x squared. Multiply and double, follow the rules. Okay, minus 4x, and then plus x squared. Okay, after I multiply this out and combine, I will get x to the fourth minus 5x squared, because I have to distribute this negative through. So that's going to be negative. This is going to be positive, and this is going to be negative. I need to pay attention to my signs. Okay, now I can see when I combine this, I will have my x to the fourth minus 5x squared plus 4x. And of course, I am differentiating from 0 to 1, so I just integrate like I know how to. Plug in my 1, and of course, my 0 value will give me 0. So I plug in my 1 value, and I will get 8 pi over 15 for the volume. Now this would be cubic whatevers, right? Because we're looking at volume. Okay, let's take a look at the next one. Is called solids of a revolution, and those were the ones we looked at, example 1 through 5, because they were revolving about a region, about a line. So in general, here is your general way to calculate that, depending on whether you're integrating with respect to x or respect to y, and that you have to pay attention to, whether you are revolving around the x-axis or revolving around the y-axis. So you want to pay attention to whichever the outer radius is. As we said before, the outer radius, pi r squared, minus the inner radius will give us that volume. And here's another example that we have here of two functions, and we're going to take this function and we're going to spin it around this said line. Okay? All right, let's keep moving. Okay, now let's look at a volume of a solid obtained by rotating the region. In example 4, about x equals -1. So we're still looking at our parabola, and we're looking at our straight line. And as we look at this, we realize we're going about the y-axis this time. So I have to solve for x and describe my values in terms of y. When I do that, I have y equals x squared was my parabola. If I'm going to solve for x, then I'm going to have x equals the square root of y. Okay, so now I have to remember when I'm using that, I'm going to have my inner radius 1 plus my y value, because this is still a line, and then my outer radius is going to be 1 plus my square root of y value when I solve it with respect to y. Here's my 1. 1 plus my y will go here, and 1 plus my square root of y will go here. Spin it around x equals -1. And then I can take a look and see, wait a minute, this is also an even function, so will that help me? Well, I'm going from 0 to 1, so I won't need to do that. So 0 to 1. And I have the area, again, with respect to y. So I have 1 plus the square root of y squared minus 1 plus y quantity squared, because we have the parabola again on the outside and the line on the inside. So after I clean that up, multiply it out and clean it up, I will get this value. I can factor out the pi, and then I can go ahead and integrate, substitute my 1 value in, my 0 will wipe it all out, and I get the result of pi over 2. And yes, you should keep your answers in terms of pi rather than putting the decimal there. And why is that? Because pi is a complete irrational number, and if you try to put a decimal, you'll be estimating at some point. Okay, so now let's take a look at volumes of two solids that are not solids of a revolution. Let's just look at two solids. Here we have some interesting figures. This is a computer generated picture. We can see if I have, looks like a circle at the bottom, and then this comes to a point. So if I were to slice this, I would get a triangle. So let's take a look at it over here. Getting a slice, I would get a triangle, and that triangle, when I take the circle to be x squared plus y squared equals 1, its base is a typical cross section. So this, if I solve for y, will be y equals the square root of 1 minus x squared. And this distance is my y distance. The cross section, this is my base, okay? So this is my base here, what I just looked at. Here's my base. The cross section is an equilateral triangle. So my equilateral triangle will have a distance of y from the center. And we know it's an equilateral triangle, so we have a 30, 60, 90 triangle here. And we can have the square root of 3 times y. Okay, so now I use the method that I looked at before. I have the area, which is 1/2 the base times the height. And my base, again, is my circle. And then my height is my square root of 3y. Okay. The volume of the solid then would be my area from -1 to 1. What do you notice here? We notice that it is symmetric of the square root of 3 times the quantity 1 minus x squared dx. Since it is a symmetric figure, I can take it 2 times 0 to 1 to simplify things, and go ahead and bring out my square root of 3 because it's also a constant. And once I integrate the inside, I will have x minus x cubed over 3, examining it from 1 to 0. And that's it. Example 7. So 4 square root of 3 over 3. All right, the next one, again, you have to really dissect, literally dissect these to take a look at what kind of figures you have. Here I have the volume of a pyramid where you have the base is a square and we're going to call the side L and the height H. So here we have the base of a square. We're going to call the side of the square L and the height of the square H. Now, in this figure 14 and 15, they set it at the origin and bring it out the X. You will also see that you could put it vertically and do it this way if you'd rather. Doesn't matter, but we are used to more integrating with respect to X than we are respect to Y, so taking a look at it this way may be easier. So we have the area of the base, which we know is a square. Now, this is back to geometry. We're going to take a look at similar figures. We have similar figures here with these triangles. So if I know my X over my H is equal to this over this, which is my S over my L. Okay, as I look at it proportionally. Now, I know that S divided by 2 over L divided by 2, I can use that because I want to look at this area. But when I divide them both by 2, they reduce anyway, so I have my X over H is equal to my S over L. And this is my similar figures so that I can use that for my formula. So now the cross-section value is going to be my side squared, S squared, which is going to be my L squared over H squared times my X squared. Now when I want to find my volume, come back down here. If I take a look at from 0 to H, okay, 0 to H, and again 0 to whatever my height is along the x-axis, I can integrate. And with respect to X, it gets confusing when you're looking at all these variables, but remember you are integrating with respect to X. And now you have to substitute in your H values. Your 0 wipes it out. So the pyramid would be L squared times H over 3. That would be your general formula for something like this. And they show you also down here how that can be done if you want to integrate it with respect to Y. You get the same answer either way. So whatever you're most comfortable with. Finally, we have an interesting looking, not that these others weren't interesting, but this is another way of looking at it. We're going to take a wedge out of this cylinder. So we have this wedge here. And we take a close look at this wedge, and inside this wedge we can have a right triangle that will help us solve using a squared plus b squared equals c squared. We have one plane perpendicular to the axis of the cylinder, the other intersects the first angle along 30 degrees along the diameter of the circle. So we have the volume of the wedge. So again, you place this where you want to place it, and we can place it along the x-axis where the diameter meets the plane. The base of the solid is a semicircle. Okay, this would be a semicircle. Again, the solid that we're talking about is just this area right here, this wedge. So we have the base of a semicircle, and with an equation that would be y equals the square root of 16 minus x squared. Okay, and x is going to be between -4 and 4. The cross section, which is perpendicular to the x-axis, which is a distance x from the origin, is the triangle ABC. And then that is the base that we get, y equals the square root of 16 minus x squared. Now the height is going to be the absolute value from B to C, which is going to be based on the 30-degree angle that is cut here. So this would be y tangent 30. So y tangent of 30 would be the square root of 16 minus x squared over the square root of 3. So the cross section then would be 1/2 square root of 16 minus x squared times this 1 over the square root of 3 square root of 16 minus x squared. And when we reduce that, we'll get 16 minus x squared over 2 square roots of 3. Now again, we're going to take a look at the volume, and we're going to take a look at the volume from -4 to 4. When we do that, we can say, oh, this is also symmetric, so we can do it from 0 to 4 and multiply this by 2, which will get rid of this 2 on the bottom, and then I'm factoring just out a 1/3 outside, leaving me with 16 minus x squared. And when I integrate this, I will have 16x minus x cubed over 3. I'm going to evaluate it from 0 to 4. My 0 wipes it out again. My 4 value will give me 128 over 3 square roots of 3. And again, I'm going to encourage you to leave these not as decimals. When you give these answers to me, don't give them as decimals. You need to give them as the radicals and leave them in terms of pi. Okay, so this is it for section 5.2. We are done with 5.2, officially done with day 16. And we have 2 more days of lessons to go, and then we're going to use this Thursday as a review.